Hi everyone, we are Team 3 consists of Donggyuri, Jinwoo-jeon, and Hoonhee-jo. This is proposal presentation for CS572 project. We will introduce learning on event sequence embedding for dense event-based deep stereo. First, introduce background and explain why we choose this paper. Then briefly introduce our reference paper and related works. Finally, we describe our plans to reproduce the results of the paper and future improvements. SLAM, simultaneous localization and mapping, can update map of an unknown environment at the same time tracking the agent's location. Especially in mobile robots, they must know what the map looks like and where they are to perform their task. There are many SLAM methods using LiDAR, large camera, and several sensors. Among them, visual-based SLAM is easy to set up and it has good performance. So they are often used in practice like beams fusion, warp SLAM, open beams, something like that. In visual-based SLAM, the robot must need information about the depth of each scene, because it can interpret three-dimensional space from two-dimensional images using depth information. Once we know the depth information, we can use it for robot applications, like constructing map or estimating robot pose. For this, triangulation in stereo vision is an efficient way to get depth information. Draw below formula, the depth can be calculated using some parameters and disparity. As you can see, disparity is difference in image location of an object seen by the left and right camera. Then, how to get disparity in stereo vision? Here's a method called stereo matching. Stereo matching is the determination of corresponding points in images. In the rectified stereo camera setup, the objective is to determine the horizontal pixel displacement between the left and right images, and it is called disparity. As I said, that disparity map can be used to compute depth map. Our reference paper proposes stereo matching method using event camera. Event camera is dynamic vision sensor and it only responds to local brightness changes. Compared with frame-based camera, it does not respond to fixed situation. Due to this mechanism, they have high temporal resolution, high dynamic range, and are invariant to motion blur as you can see in the right video. Therefore, we plan to reproduce the performance of the reference paper compared to frame-based methods. Also, the paper lists several drawbacks and limitations of event camera. One of them, events only occur at different intensity like edge of object, so disparity map becomes sparse. Then it leads to a slam of bad performance. Although this paper has solved it, but there is still ill-forced problem.
The paper we chose is Learning on Event Sequence Embedding for Dense Event-Based Deep Stereo, which is published in ICCV 2019. Its main idea is getting depth information from stereo event sequences through end-to-end learning. And their contributions are twofold. This paper is first approach using deep learning for event-based depth estimation. Also, they propose a learnable representation for event sequences, taking into account 2D spatial and 1D temporal dimension. Long story short, the network proposed in this paper want to compute an estimated disparity map from stereo event sequences. The proposed network architecture consists of 4 modules: embedding, matching, regularization, and estimator. Let me describe the overall flow briefly. The embedding module takes left-right event sequences and computes each descriptor independently. The matching module then takes the left and shifted right descriptors, computing a matching signature. The regularization module is an algorithmic neural network with 3D convolutions and shortcut connections. Lastly, estimator produces an estimated disparity for each pixel, like the above equation. One of the main contributions of this paper is that temporal embedding. So what is embedding? Embedding means the process of aggregating the discrete raw data to the continuous vector for the network input. However, unlike frame-based one, event needs to be carefully embedded since they are spread across both space and time dimensions, as you can see in the left figure. For that, this paper proposed the composition embedding using novel temporal aggregation. It is defined per location and takes a local event sequence as input and produces an event image, as you can see in the right figure, similar to the general camera image. This is a proposed temporal aggregation method using first in, first out queue. It is a 4D tensor, each dimension for timestamp, polarity, and spatial dimensions. It stores k most recent events at each location in order of arrival. This implementation has a strong advantage for handling the event sequence, regardless of the amount of motion. Event timestamps are continuous and sampled irregularly. To deal with this problem, they proposed a continuous fully connected layer. As you can see in this figure, in contrast to FC, CFC allows to embed irregularly time-spaced event sequences and make the whole network be trained in an end-to-end manner. This figure shows the qualitative comparison of the proposed method with recent event-based method on the indoor flying dataset using drone. You can see the depth estimation is more accurate than other algorithms. Actually, event-based methodology has recently begun to attract attention, and there are not many related studies yet. The current state of the art is the proposed method in 2021, which leverages event-to-image translation. However, there is not much performance difference between this SOTA and the method we introduced today. Also, there exists several expansion possibilities to improve, and each code is publicly available. So we chose this paper as our baseline.
Let me explain the plan to reproduce the performance of the baseline paper. In the baseline paper, the authors used the MVSec dataset published in the RL journal to use the event data of the stereo setup. The data is now publicly available so that we can use it. For the dataset, the authors on the dataset paper use two Davis cameras that provide both online event and images. Two cameras were installed in a stereo setup, and the ground truth for depth was occurred using LiDAR. In addition, considering the application, this system was mounted on the drone and data was occurred through the drone while driving. The code of the paper, which we target, is also open to the public. It's on GitHub, so we plan to use this code. The code contains a part that converts event into a Q-type and embeds from the Q-type of event into the image type of event, which is an important module for us. The current base code uses the most practical stereo matching network as presented in the paper, and we plan to modify the stereo matching network part. Let me explain the performance improvement plan. As suggested in the previous study, event data has semantic information about the edge part. So it is effective for stereo matching because the information that cannot be obtained from images can be obtained. However, as mentioned before, stereo matching with only events has a disadvantage as an ill-posed problem. We want to improve the performance of the network by converging events and images with different modalities. We want to receive both events and images from the left and right cameras in one network, and finally, extract an accurate and dense disparity map. First, we plan to develop a fusion module for improvement. Previous works changed the event data into an image from through the embedding module, but the modality of an image and event are still different. To combine these two data with the different modalities into one picture map, we propose an attention map. Simply concatenating two picture maps is not sufficient to fuse both data. We created an attention map that selects the required area from the image picture map. The network can take advantage of both data by properly combining the attention map and the event picture map. For areas where events are robust, we plan to get help with stereo matching from events, and for areas where images are robust, we plan to get help from images. And since it is important to obtain spatial correlation in stereo matching, we plan to calculate the correlation between features of multiple scales. We plan to create the multiple scale features from both input data and fuse each to consider order from coarse features to fine features. Feature maps of multiple scales generated in this way are generated from each of the left and right cameras. Thank you for listening.